Assume you throw a die n times, and you want to know what is the probability for getting a certain number of sixes. These figures show the probabilities for 5 dice, 10 dice, 20 dice, and 100 dice. You see that for 20 dice, getting 3 sixes is the most likely. And if you throw 100 dice, getting 16 dice is the most likely. This is a binomial distribution. But you see here that as n increases, it resembles more and more a normal distribution. The same thing happens, for example, if you throw a pin. Assume that the probability of getting a pin up, if you throw a pin, is 40%. Then these figures show the probabilities of getting a certain number of pin up, if you throw 5 pins, 10 pins, 20 pins, and 100 pins. And for example here for 20 pins, you see it's most likely to get 8 pins up. But also here you see that the distribution resembles more and more a normal distribution. So for large n, a binomial distribution resembles a normal distribution. And the same thing also happens for hypergeometric distribution, and also for some other probability distributions. And that we're going to use now when we want to find an unknown proportion or probability. And let P be some unknown probability for a certain event to happen, or for some unknown proportion of objects having a certain property. For example, the event could be getting pin up on a pin, or for example, the person is a smoker. So here we are seeking an unknown probability for this to happen, and here we are seeking an unknown proportion of a population that has this characteristic. Assume you do a sample, then this event or characteristic occur x times when you do a sample of n, that is n observations. Then your estimate of the unknown probability or proportion is x divided by n. One can show that this random variable given by this has an expectation value of p, that is the unknown probability, and the standard deviation given by this expression, where again p is the unknown probability and n is the sample size. Further, you can show that the estimation of p is normally distributed for large n, and as a rule of thumb we will here use n larger than or equal to 30. So this is normally distributed, and to that corresponds a standard normal distributed random variable, this one here. And this has the same structure as we had before. For example here, this is our estimate of p, as this was our estimate of the expectation value. And here is the unknown parameter, and here's also the unknown parameter. And here we have the standard deviation, and this is expression for standard deviation. So this one here is standard normal distributed. Then we have a confidence interval corresponding to that, again given by the probability 1 minus 2 alpha. That's the probability for the unknown p, probability or proportion, to be in the following confidence interval. So this one here. And this also has a similar structure to what the other confidence intervals we have seen before. And here are our estimate of p based on our sample. So assume you have thrown a pin 100 times, and you got a pin up 57 times out of those 100. Then the estimate of the unknown probability of getting pin up is 57 divided by 100, so 57%. Say we want to give a confidence interval with probability 95%. This corresponds to alpha being equal to 2.5%. And then set alpha you can read off from the set table, since we're seeking set alpha. And then you will get 1.96. Then according to this, we will get the confidence interval. So if you put in the numbers we have, then we get this confidence interval, which is this. So with 95% probability, the true probability of getting pin up is between 47 and 67%. So let P be an unknown proportion of people voting on a political party. If you do a random sample on 1,000 people, then let X be the number of people voting on this political party among those 1,000. And assume this is 170 in this sample. Then we want to estimate P based on this sample. Then the point estimate is given by 170 divided by 1000, so 17%. And for interval estimate, we use the confidence interval with the probability equal to 95%, which corresponds to alpha 2.5% and set alpha 1.96. Then we get from this confidence interval formula for our values the following confidence interval, which can be rounded off to. With 95% probability, the unknown proportion voting for this political party is between 14.7% and 19.3%. Now this is quite wide interval, so if you want the width on this interval being smaller, for example 0.2%, then how large must our sample be? Then just doing as before, taking this endpoint minus this one, then we can find the length from this expression. And here we can solve for n, and that will give us, and if we put in our numbers, and we wanted a width of 0.2%, which is this, and squared, which gives roughly 500,000 people. So if you want a width as small as 0.2%, then you must have a large sample. For example, if the Norwegian population, this would be 10% of the whole Norwegian population. So this is probably unrealistically large sample size. If you are instead satisfied with the width of 1%, then you instead have to ask 22,000 people, which is more realistic.